Okay, it's time for discussion 2-2, physical and chemical properties and changes, and we're going to look at some important groups on the periodic table. All right, so let's first talk about physical versus chemical properties. A physical property is a property that you can identify without changing the nature of the substance. In other words, they're properties that we can measure with our five senses. So things like mass. I can measure the mass of an object by putting it on a balance. I don't have to change what the object is to do that. I can measure volume by either length times width times height, or using something like a graduated cylinder. I can determine color simply by looking at something. I can determine the dimensions of something by measuring it with a ruler. I can test how hard something is by smashing it with a hammer. Physical properties are properties that we can measure without changing the identity of the substance. So chemical properties are the opposite. They are properties that can only be identified by changing the chemical ID of the substance. In other words, they're properties that can only be measured when the substance undergoes what's called a chemical change. All right, so examples of chemical properties, things like flammability. Burning something is a chemical change. You can only tell how well something burns by burning it. Toxicity, when poisons interact with the cells in our body, those are chemical changes that are occurring. You can only tell how toxic something is by ingesting and digesting it. Chemical reactivity is how well things react or how vigorously they react. You can only tell that by undergoing chemical reactions. And half-life is actually an example of something that's a chemical property, because we actually have to change in order to measure the half-life, we have to undergo radioactive decay, which changes the nature of the element. In many cases, radioactive decay actually creates brand new elements in the process. All right, so there's two different types of physical properties, an intensive and an extensive property. An intensive property is one that is independent of the sample size. So intensive properties will always remain the same for a given substance. Because they're always going to be the same for a given substance, they can be used to identify a substance if we didn't know what it was. For example, color is intensive. Doesn't matter if I have a huge chunk of copper or a small piece of copper, they still have the same color. They still have the same boiling and melting point. They still have the same density. They still have the same specific heat. We'll talk about what that is later in the year. And they still have the same smell. Doesn't matter how much of the substance we have, the property will always remain the same. Extensive properties are the opposite. They are properties that change as the sample size changes. So think things like mass. If I add more matter, its mass will increase. If I add more matter, its volume will increase. If I add more matter, its length will increase. So the reason why we can use an intensive property to identify something is because we know that that property will always be the same. So let me give you an example. We have an unknown liquid. It's a clear, colorless liquid. It has a mass of 10 grams. Is just knowing what its mass is enough to identify what it is? A lot of things could be 10 grams. I have a sample of a clear, colorless liquid. It has a volume of 30 milliliters. Also, not enough information to identify it. But if I said I have a clear, colorless liquid that has a density of 1 gram per milliliter, a specific heat of 4.18 joules per gram degree Celsius, a melting point of 0 Celsius, and a boiling point of 100 Celsius, I would know I was talking about water. All right, so now let's talk about physical and chemical changes. Very similar. A physical change is a change in which the chemical identity of the substance remains the same during the change. So over here I have triangle plus square. After the change, I have triangle plus square. For physical changes, think of things like phase changes. I could have frozen water, it's called ice, but it's still water. If I add heat to it, it'll melt, which is a phase change, but when it's melted, it's still water. I could further add heat to it and make it boil. Well, then we call it water vapor because it's still water. So phase changes, all they do is take something from solid, liquid to gas and back. doesn't actually change what the substance is, so it's a physical change. Dissolving is a key word that you should think of to indicate a physical change. A lot of kids get that one confused. If you dissolve salt in water, when you taste it, it tastes like salty water because at the end of the change, it's just salt and water mixed together. Bending something doesn't change what it is, so that would be an example of a physical change. Stretching does not change what something is, nor does cutting it. Now, if we think of a chemical change is one in which the identity of the substance changes. In other words, brand new substances are made. So, for example, I could have a molecule of square triangle. After the change, I have individual atoms of square and triangle. Remember, atoms will have different properties than the compounds that they make. So think of things like burning. Wood burns and becomes ashes and smoke. Iron rusts and becomes a compound called iron 3 oxide. A bomb explodes and it goes from fuel and a fuse to a bunch of debris. Oxidizing is a reaction with oxygen, so some things will oxidize more than others. So we would have to actually react with oxygen to see, okay? So chemical changes are one in which brand new stuff is made. All right, so what is our evidence that a chemical change occurs? There are four main pieces. One is we see a change in color. Now, when I say a change in color, I don't mean like painting something a new color. I mean like take two clear liquids and mix them together and all of a sudden it turns pink. That is a change with a change in color I'm talking about. If that happens, a chemical change has occurred. Another is a change in temperature. Well, I don't mean take a sample of water and heat it up with a flame. I mean mix two chemicals that are at room temperature together and they get hot or get cold. That would indicate that a chemical change has occurred. Production of a gas. If you mix two things together, think the baking soda volcano, and a bunch of bubbles appear, that tells you that a chemical change has occurred. And finally, production of an odor. So our gasoline in our cars has some sulfur in it. And when it combusts in our engine, it combines with oxygen. So if you've ever smelled rotten eggs on the highway, that is the smell of sulfur dioxide. When the sulfur in gasoline combines with the oxygen, it makes that compound. We can all of a sudden smell it. So we know that that's a chemical change that's occurring in the engine of a car. All right, so let's turn to the periodic table. We know that groups are the columns in the table. There are four groups for which you must know the name. So of course, groups are important. This is review from Unit 1. Because we know elements in the same group will have share chemical and physical properties and will also have the same number of valence electrons. Now, elements in the same group don't share all of the same physical properties. We know that their masses increase as we go down, but the important bit is that they all react the same. So the first group you have to name are called alkali metals. Those are the metals in group 1 of the periodic table. So lithium, sodium, potassium, rubidium, and cesium are known as alkali metals. Group 2 are alkaline earth metals. Now, those are reactive as well, but they're not quite as nasty as the alkali metals. I'll show you some examples of the reactions of these in class. Halogens are the name we give to group 17. So halogens are very reactive nonmetals. And group 18 we already talked about are called noble gases. They're noble because they're very, very stable. They don't mix with other elements on the periodic table, much like the nobles did not mix with the commoners back in medieval times. All right, so again, group 1 we call alkali metals, and those are lithium, sodium, potassium, rubidium, cesium, and francium. Group 2 are called alkaline earth metals, and they are beryllium, magnesium, calcium, strontium, barium, and radium. The rest of the groups, these groups you don't have to worry about. Group 17 are called the halogens, and they are fluorine, chlorine, bromine, and iodine. There is one more element under iodine called astatine. It does not count as a halogen because it is not a nonmetal, just so you know. And group 18 are known as the noble gases. Those are helium, neon, argon, krypton, xenon, and radon. All right, so other ways the table are broken up is into metals, nonmetals, and metalloids. So we can see that all the elements in the F block and most of the elements in the table are metallic in nature. Now, metals and nonmetals are the opposite of each other in every single way. So metals live over here on the left side of the table. Nonmetals live on the right side of the table, with of course the exception of hydrogen. Now, right in between metals and nonmetals, we have what are called metalloids. And metalloids are elements that are kind of metallic in nature, but also kind of non-metallic in nature. Most periodic tables have a little stair-step line that goes down there. We start at the top left corner of the P block and go 1 stair, 2 stair, 3 stair, 4 stair, 5 stair, all the way down. So the elements along that stair-step line, for the most part, are metalloids. Now the metalloids are shaded here in purple. There are 2 exceptions. One metal, which is called polonium, and up here in this box we have aluminum, are not metalloids even though they live on the stairs. All right, so let's go ahead and summarize. Metals are on the left of the stair-step line. Metals, we know, tend to be solids. They're good conductors of heat and electricity. They're malleable, which means they can be hammered into flat sheets. They are ductile, which means they can be drawn into wires. And they have luster, which means they're shiny. Now again, nonmetals are the opposite of metals in every way. So if metals live on the left side of the table and are solids, conductors, malleable, ductile, and lustrous, the nonmetals live to the right of the stair-step. Instead of being solids, they tend to be liquids and gases. They're not good conductors, so we call them insulators. And they're not malleable, ductile, or lustrous. If they are solid, think of things like carbon and sulfur, they're very brittle. So if we smashed them with a hammer, they would crumble into powder as opposed to being hammered into a sheet. So metalloids live along the stair-step line, and they will share some properties of metals and some properties of nonmetals. One big property is metals are conductors, nonmetals are non-conductors, so metalloids are semiconductors. One metalloid, silicon, is what is used to make computer chips. And finally, the transition metals are just the metals in the middle of the periodic table, so groups 3 through 12 on the periodic table. All right, finally, I want to talk about dot structures. You may remember this slide appeared in Unit 1, but we saved it until now. So let's look at 4 different elements. Now, a dot structure, all it does is show how the valence electrons within an atom are distributed. Electrons in the valence shell are shown as dots around the symbol of the atom, which is why they're called a dot structure. So if we look at lithium, we know lithium is in group 1. That means it has 1 valence electron. To do the dot structure, we draw the symbol for lithium and put a single dot around it, showing that there is 1 valence electron. Now, when we're distributing electrons, it's always good to pretend like our symbol is in a box and distribute 1 electron at a time before we start pairing them up. So we're basically going to be following Hund's rule here when we do this. So for beryllium, it's in group 2. So we know it has 2 valence electrons. When I do the dot structure for beryllium, I draw the symbol for beryllium and put 2 dots around it to show it has 2 valence electrons. Carbon is in group 14, so we know that it has 4 valence electrons. To do the dot structure, I draw the symbol for carbon, C, and I distribute 1, 2, 3, 4 dots around the carbon atom, the carbon symbol, to show that it has 4 valence electrons. Now, every element in that row beyond carbon will have some pairs. So let's look at oxygen. Oxygen is in group 16, which means it has 6 valence electrons. So when I do the dot structure, I'm going to need the symbol for oxygen, and I'm going to have to put 6 dots around it. Again, follow Hund's rule. So one dot on top, one dot on side, one dot below, one to the left. Now that we have 4, we can start pairing up the other 2. And this is the dot structure for oxygen. It's really important to follow that rule when we're distributing the electrons. And you'll see that in Unit 3 when we talk about how atoms bond together. And that is it for discussion 2.2. Thank you so much for watching. Any questions you have, you can bring to class. And I'll see you there. Bye-bye.